We end chapter 3 with one more section dealing with some functions that we haven't seen before, and then also what their derivatives are. So this is going to be a short section for us, and just to let you know, at the beginning of this, you are not going to be required to memorize these functions or their derivatives for this class. It's rare that you're going to see these used in the calculus sequence, but it does just put an end to the whole chapter 3 of all of the functions that we can consider and their derivatives. So these functions are hyperbolic functions, and these result from combinations of exponential functions. And they behave in a periodic way like the trigonometric functions. They are used to model different physical objects, like wires hanging between two telephone poles or the velocity of ocean waves. The hyperbolic cosine function was also used to model the Gateway Arc in St. Louis. So here are the definitions of the hyperbolic functions that we can start with. And this is what you can see by what I mean about combinations of exponential functions. The hyperbolic sine function, hyperbolic sine of x, is equal to e to the x minus e to the negative x divided by 2. And then the hyperbolic cosine function, hyperbolic cosine of x, is equal to e to the x plus e to the negative x divided by 2. The other four hyperbolic functions are just combinations in the same way, but they actually follow the same identities that we saw with trigonometric functions. So by definition, the hyperbolic tangent of x is just hyperbolic sine of x divided by hyperbolic cosine of x. And then with the remaining three, these are all reciprocals of the three that are above. So hyperbolic cosecant of x is the reciprocal of hyperbolic sine of x. Hyperbolic secant of x is the reciprocal of hyperbolic cosine of x. And then hyperbolic cotangent of x is the reciprocal of hyperbolic tangent. So these have some similar relationships that we saw with trigonometric functions, which means there are also going to be some identities. So here are some identities that follow. The first two, these would involve hyperbolic sine and hyperbolic cosine of a negative input. So this relates to even and odd functions. The next two look similar to the Pythagorean identities, but there are some sign differences there, meaning instead of a plus that we would expect between cosine squared and sine squared, with hyperbolic cosine squared and hyperbolic sine squared, there's a negative. And then there's also some sum identities. So for the derivatives, we can actually do one for hyperbolic sine of x, just to see how this works. So if I want to find the derivative with respect to x of hyperbolic sine of x, that's really just the same thing as the derivative with respect to x of e to the x minus e to the negative x divided by 2. We don't need to use a quotient rule or anything because the division by 2 is just a constant. So this just turns into the derivative with respect to x of e to the x minus the derivative with respect to x of e to the negative x divided by 2. The derivative with respect to x of e to the x is just e to the x. And then by the chain rule, the derivative with respect to x of e to the negative x would be a negative e to the negative x. But we can just simplify that by writing plus e to the negative x divided by 2. And if we compare that with one of the ones that we saw above, that's just hyperbolic cosine of x. So that's summarized right below. The derivative with respect to x of hyperbolic sine of x is hyperbolic cosine of x, which again, that reminds us of the trigonometric functions that we saw earlier in chapter 3. There are some differences though. The derivative with respect to x of hyperbolic cosine of x is positive hyperbolic sine of x. The derivative with respect to x of hyperbolic tangent of x is hyperbolic secant squared of x. That again is similar. And then these next three, there is a difference with the derivative of hyperbolic secant of x. Notice there's a negative there. So we see that there are some sign changes. What once was negative is now positive. What once was positive is now negative. So there are some differences with these. And they could all be proved in the same way that I just showed with hyperbolic sine of x. So then for those functions, there are of course going to be inverse functions, and we shouldn't be surprised that if they're all defined using exponential functions, then their inverses should be defined using logarithmic functions. So we can see that here. Here's the inverse of hyperbolic sine of x. That is natural log of x plus the square root of x squared plus 1. That's for all real numbers x. The inverse of hyperbolic cosine of x is the natural log of x plus the square root of x squared minus 1. And that's for x greater than or equal to 1. And then finally, the inverse of hyperbolic tangent x, that's the natural log of the quotient 1 plus x divided by 1 minus x. And that's for x between -1 and 1. We really only bring up those three because we will see some things looking like that as we get into chapters 5, 6, and 7 of this calculus book. And then using those definitions for the inverse, we can obviously find their derivatives just by thinking of the derivative of the natural log function and then the chain rule. And so we have the derivatives of those three inverse hyperbolic functions written right below. So again, we don't need to memorize all of those things, but they're gathered here in this video for your reference. Let's just look at one example to see how these derivatives work. So find the derivative of f of x equal to e to the x hyperbolic cosine x. So f prime of x would be the derivative with respect to x of the product of those two. So we have to use the product rule, which means the derivative with respect to x of e to the x times hyperbolic cosine of x plus the derivative with respect to x of hyperbolic cosine x and then times e to the x. And this just turns out to be e to the x hyperbolic cosine x plus the derivative of hyperbolic cosine x we have right above. It's hyperbolic sine of x times e to the x. So we could say that this is e to the x times hyperbolic cosine plus hyperbolic sine. That's it. That's our derivative. But one thing that we can notice from these derivatives is a different way of approaching them. So written at the end of this lesson, I have that same example, but instead of taking the derivative first, I just noticed that if we have e to the x times hyperbolic cosine x, that's the same thing as writing e to the x times the fraction e to the x plus e to the negative x divided by 2. Distributing e to the x to the numerator would give me e to the 2x plus 1 divided by 2, which ends up just being 1/2 e to the 2x plus 1/2. If you take the derivative now of this expression, you would just end up with, as you can see here, by the chain rule, e to the 2x. So it turns out that the derivative has a couple of different forms. There's e to the 2x, and there's also e to the x times hyperbolic cosine plus hyperbolic sine. If you want to see why those two are connected, we can just go back to our first answer and combine what we had for hyperbolic sine and hyperbolic cosine. You can see that you're just going to be adding those two. So if I am going to add these two, then I would have e to the x plus e to the negative x divided by 2 plus e to the x minus e to the negative x divided by 2, which means the e to the negative x's are going to cancel, and I would have 2 of e to the x over 2, so that's just going to end up being e to the x times e to the x, which is e to the 2x. So all of this stuff is just manipulation of manipulations. That's all it is. So this is why I'm not requiring you to memorize this. This is just, we're taking things to the end of all of the stuff that we've seen and just looking at some derivatives and some inverse functions.